The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
All right, I think we're gathered, so let's get going. We were going to start DAEs today, but we decided to postpone for one day and do a little catch-up on different things that you should know. And I thought I'd first back up a minute and talk about, recall what you've learned so far. So we started out talking a lot about linear algebra, and particularly the problems of this type, where you're given a matrix and you're given a vector, and you want to figure out what the x is that makes this equation true. And you've become extremely familiar with the convenient MATLAB backslash function. You've probably used this a lot of times. And if you remember, this is one of the only problems where we often have a unique solution. We know a solution exists, and we can do a finite number of steps in order to get the solution. And actually, the method we have is really good, so it almost always gives us a solution and to machine accuracy. So this is a brilliant method. And so everything is based on this in our whole field, actually. So we learned this first. We learned it takes, n cubed operations in order to get the solution, where n is the size of the vectors. And when we do the solution, the x we get for backslash invariably, if there is a solution, solves this equation to machine accuracy in the sense that you multiply m times x, you get b, to as many digits as you can read. However, we talked about how m can be poorly conditioned so that there might be multiple x's that would solve this equation to machine accuracy. And so that's the problem with conditioning. So it's not that it doesn't solve the equation, it's that we're not really sure that's the right x. You could get a bunch of different x's that basically solve it as well as we can tell. All right, so you guys remember this? All right. And so that also implies that if you make a very small change in b, you might get a gigantic change in x. Because even for 1b, you have quite a range of x's that could work. All right. Then we tried to solve problems like this. Right? Systems of equations, not just linear ones, but nonlinear ones as well. And what we decided to do as one of our best methods is NewtonRaphson, where we keep on doing j backslash f, right? Actually negative f, right? So all we did in this method a lot of times is we just kept on calling this method over and over again. All right, so this took order of n cubes. This thing's going to take order of n, I don't know what you call it, steps or something. Maybe you guys have a word for it. What do you call the iterations? Iterations. So it takes the number of iterations times n cubed. Now, if you really can make NewtonRaphson work, and you have a really great initial guess, the number of iterations is really tiny because NewtonRaphson is such a fantastically great convergence. However, we're usually not such good guessers, and so it might take a lot of iterations. And in fact, we use the dogleg method to solve this, as we discussed about, where you mix up different methods and you have a truss region and all this baloney. And so it might actually be quite a lot of iterations to get there. And then we went and tried to solve this problem. And what we decided to do for both of these was almost do the same thing. So say, well, we can really solve this one by instead solving right? That's really what we ended up doing. That's what happens inside fsolve, is it converts the problem of finding fx equals 0 into a minimization problem to try to make the norm of f as small as possible, because the answer will be when the norm is 0. And if fx equals 0 has a solution, then the global minimum here is a solution. As long as your initial guess is good enough that you're in the valley that leads to the true minimum, then this will work. And that's actually what fsolve does. So these two guys get kind of coupled together, the minimization problem and the root finding problem, or the problem of solving systems of nonlinear equations. And in both of them, we're going to call the first method a million times. Okay? So that's the way we're working so far. And actually, when you do FMINCON, which is the next level, then you actually end up looking for saddle points, which again we look for as minimizing the norm of a gradient squared, which gets it back into this kind of form. And so they're all the same thing. All right? And you can, again, work out estimates of how much effort it takes. And it's something times n cubed. Typically, if most of your work is this. Now, I should make a comment that in practice, that's not always true. So in practice, sometimes, although the highest order term is n cubed, the linear algebra programs that do this are so great that the prefactor is tiny. So in order to get the limit where the n cubed term would actually dominate the CPU time, you have to have a gigantic n. And in fact, the limit is often the effort to construct the matrix, J, and so it really goes as n squared. So although this nominally is like n cubed, in practice, a lot of times it's n squared. Okay. And the same for these other methods. And then a lot of them get into how good the initial guesses are, because the number of iterations can get crazy. And in fact, maybe it never converges if your initial guess is bad. So that can be a really critical thing to make this better. Because you can't change n. You know, I mean, how many unknowns you got is how many unknowns you got. But you can change the number of iterations by, say, more clever initial guessing. And that was the whole concept about continuation and homotopy and all this kind of stuff, was trying to help reduce this number. Last time, we talked about implicitly solving ODEs. And so we had an update formula. So we were solving an ODE initial value problem. Right? And you know, we said that first we went through the explicit methods, and they're like perfectly straightforward to do, and you don't have to solve any systems and nonlinear equations to do them, and so that was great. But then we pointed out that a lot of times they're numerically unstable, and so then you have to instead use implicit methods. But the implicit methods generally work this way: that you have your new value of y you're trying to compute is your current value of y plus delta t times sums g. It depends on the size of delta t and y old. No, y new. Maybe y old also. And these g's are things like the Crank-Nicholson, which you're going to work on in the homework. And we showed in class too. And so there's different update formulas that people suggested how to do this. The trick of this is that the y new is inside the function. So therefore, this is really another problem like we had before. You can really rewrite this that way by just putting this on the one side. Put them on one side, have a 0, and now I'm trying to figure out what y new is. And I'm going to solve that using this method, and I'm going to solve that by using this method. All right, so now how does the scaling going to go? At each time step, I have to solve one of these guys. How much effort did that take? We did that, right? Here it is. N iter times n squared. And then how many times do I have to do it? Right, so it depends on how many time steps I have. So how small my delta t is. So it's like something like t final minus t naught over delta t. That's the number of time steps if I have constant delta t. Times number of iterations that it takes to do the nonlinear solve times n squared, which is the cost of forming the Jacobian matrix. Now, this can be pretty large. So as we talked about, this might be as big as 10 to the 8th in a bad case. certainly be less than 10 to the 8th, because otherwise you'll have numerical problems. Maybe it's really going to be 10 to the 6th for a real problem. So you have 1,000,000 time steps. At each time step, you have to solve the number of the solve costs this much. Number of iterations might be what? How many iterations do you guys take to solve nonlinear equations? You've solved a lot of them now. How many iterations did it take? 10? Does that 10 sound right? You have a good initial guess, 10. If you have a medium initial guess, maybe 100. If it's more than 100, you're not going to converge, right? Yeah, okay. So this is order of 10 maybe. So 1,000,000, 10, and then n squared. It just depends on how big your problem is. So in my group, the problems we typically do, n is approximately 200. So this is like 200 squared. Okay, and now you can see that the number of iterations, and maybe this is maybe a little bit overestimate. Maybe I can get away with 10 to the 5th. Something like that. But you can see it starts to get pretty big. But for writing it, as you guys are writing software, it's not that big a deal. So I can assign it as part 1 of a 3-part homework problem, is to write an ODE solver that solves implicit equations. And you can write it, and the reason you can is because you've already written methods that solve this. Actually, MATLAB did it for you, but you could write it yourself. I assigned it to the 1010 students. So you write this, the backsub solution, to solve the equations, and we've already wrestled this. I think you guys wrote one of these yourself, and also we can use fsolve, which is just another little bit better implementation of the same thing. And then now you write your next level, and so you can see you're doing a composite process where you're doing something at the top level, it's calling something at a lower level, that's calling something at a lower level. And then what you really have to be concerned about if you're worried about CPU time or whether the thing's going to solve before the homework is due is how big does this get? How many operations are you really asking the computer to do? Now, remember, the computer is fast, right? So it can do a gigahertz or something. So you can do like 10 to the 8th somethings per second. And what should I say about this? I have not included, but I should, that it's, well, I'm assuming here that the function evaluation is sort of order n of how many variables they have. Okay, sometimes function evaluations are much more difficult than that, primarily because sometimes they're actually including further nested stuff inside. So your f is actually coming from some really complicated calculation itself, and then then you have another big giant factor of how much it costs to do f. But I'm just right here. I'm just assuming it goes as n. All right. So actually, let's just multiply this out. So this is what 10 to the 4th, 10 to the 10. So this is like 10 to the 10. 10 to the 10 kind of flops. But your computer does 10 to the 4 times 10 to the 9 per second. Is that right? That's what I told us, 4 gigahertz? Yeah. So this is really not bad, right? This is a few seconds on your computer. So that's why you can do these homework problems, and you still get them done. And if you have even poor implementations, it takes 1,000 times longer. It's still 1,000 seconds, 20 minutes on your computer. Okay? So you're okay, but you can see we're starting to get up there, and it's not that hard to really make it a big problem if you do something a little bit wrong. All right. And just a notation thing. A lot of these things we're doing are writing software that takes as input not just numbers or vectors. So those are things that we call functions, right? Things that take a number or vector as an input and give you, say, a function, a number or a vector as an output. But oftentimes we actually want to take the names of functions as inputs. So for example, the root finding problem, it takes as input what is f, right? You have to tell it the name of a function for fsolve to be able to call it. So fsolve is an object that takes as input the name of a function. And things that do that are called functionals. Functionals. So, for example, this one is x is equal to this root finding functional, fsolve. And I'm going to write with square brackets. It depends on f. That's it, right? It depends on f. So you give it the function f, and if fsolve is good, it should be able to tell you what the x is. Now in reality, we help it out. So we give it x naught 2, just to give it a better chance. All right. I write the square brackets just to indicate that one of the things inside is a function, not just numbers. All right. We do this a lot. So you guys have done this since you were kids. So derivatives, yeah, ddx of f, right? So we have, I don't know, for example, grad of f, right? That's a functional. The grad, the symbol means the operator, the functional. It operates on functions. You can write a general gradient function that takes any vector valued, any scalar valued function and computes the gradients with respect to the inputs, right? This week we give you one that computes a Jacobian. Give it any f of x, it gives you the Jacobian of f with respect to x. Okay, so that's a functional. So anyway, we'll do a lot with functionals. You've been using them all the time. I'm just trying to get you to think about it abstractly. And then there's a whole math about functionals. And there's a whole thing called calculus of variations. It's all about if the objects you're worrying about are functionals, not functions, then you have another whole bunch of theorems and stuff you can do with that, which you'll probably end up doing before you get out of this place. But I'm not going to do that right now. All right. I would comment that one kind of functional that's particularly important to a lot of people in your research is the fact that the energy of any molecule is a functional of the electron density. And this is the basis of what's called density functional theory. And so this is why a lot of people, many of you included, are going to end up using computer programs that are trying to find what the electron density shape is. Things on molecular orbitals and stuff, you've probably heard of these before. And there's a functional that gives the energy of the molecule, and what you care about mostly is energy because that connects to all your you're doing 1040 is all about the energies, right? And once you know all the energies, you can actually compute the entropies and all kind of stuff too. And so this is one application that's really important. It was a little bit surprising that this was true and be able to be proven to be true. And so the guy who did that got the Nobel Prize. His name is Kohn a few years ago. All right. Actually, in liquid phase stuff, if you work with Professor Blankstein, they also have a version of this for properties of solution. And where it's not the electron density, but it's actually the density of the material in the solution phase. Maybe Professor Swan too. You guys do that? Yep. So you work with Professor Swan, you might learn about that too. So that's one where the actual functional is like a big focus of the entire project. And the key is that this is a function. The density is a function of the position. And then the functional converts that into a number, E. All right. It's all page 1 here. Now I'm going to sort of change topics, but it's related, is about the connections between numerical integration, interpolation, and basis functions. These things are all like intimately tied up together, so I'll try to show you. So we're trying to solve a numerical integral. And then let's think of what we're really doing. When we're doing this, we typically only do a few function evaluations. So we have a few points where we know the numbers f of t n. We picked at a few t's, we evaluated f. And from those few points, that small number of function evaluations, we want to get a good estimate of this whole integral. Now it's a little goofy actually if you think about what we're trying to do. So suppose we're trying to do an integral from -1 to 1. We have some function that has a point here, a point here, a point here. And just for concreteness, so let's say this is 1 over 26, and this is 1, and this is 1 over 26. And I have a particular function in mind that has those 3 points. Now, first thing to keep in mind is there's an infinite number of functions that go through those 3 points. Right? Now, what we've been doing is we've been fitting some function to these points, and then integrating that function that we fitted. Right, so when you're in high school, you did the rectangle rule, and what the function was that you used was this and this. And you knew the integral of this function and the integral of this function, and you added them up, and you decided from the rectangle rule that the integral was equal to 1 and 1/26. Okay? But then some other people in high school were a little smarter, and they said, you know, it's not so smart to start at the end. Just, this thing was symmetrical to begin with, and now I'm fitting it with a function that's like wildly unsymmetrical. So let's instead not evaluate those points. Let's instead evaluate the midpoints, and maybe we find out that the midpoint values are here and here. And so I would assume that the function is just a flat line. That kind of looks not so good either, because it doesn't go through these points. But anyway, for the 2 points I knew, if I only used those 2 points, that would be the midpoint method. And I would get the I midpoint method, and I get something, and I did it for this particular function I have in mind, and it was 8/29. And then some other people say, well, let's use the trapezoid rule, so let's approximate the function as this over the interval, which looks kind of sensible. And if you do that, it turns out you get the same number as you do with the rectangle rule. So I trapezoid. Now, let me just, as a warning, if you just did the rectangle rule and then the trapezoid rule and you got the same number both times, you might be tempted to conclude you've converged and you have the true solution because you did 2 methods of completely different orders and you got exactly the same number and you're super happy and you're ready to publish your paper. Okay? But of course, the function might not look like this. So the particular function I had in mind was f of t is equal to 1 over 1 plus 25t squared. Okay, that was just the function I had in mind. And the way that function looks like is like that. And the real integral of that function, which you guys, if you remember how to do it from high school, you can actually evaluate that integral. It's like nothing to do with either 8/29 or 1 and 1/26. It's something completely different. Now, those of you who went to really advanced high schools, you also learned Simpson's rule too. And Simpson's rule said, let's fit it to a parabola. And so that would give you something like this. And if you do Simpson's rule, I ended up getting this if I did the arithmetic right. 1 1/3 plus 2/78. Who knew? Okay. Which also has little relation to the true value of the integral. Now, if you're smart and you did trapezoid and then compared it to Simpson's, then you say, oh my goodness, these are not really that similar, and so I'm not converged yet, I better do something else. Okay? So I just want you to be aware, when we do these rules, what we're actually doing is we're fitting our points to some continuous function that we know how to integrate. And then we do the analytical integral of that function, which is a fine thing to do. But just be aware that it's like extrapolation. It's like we're imagining what the function is doing between these points when we actually we haven't tested it. Now we could just call more points, right? We could calculate, but that would cost us more function eval, and we're kind of trying to save our computer time. So we want to finish up before the TG so we can go buy some beer. And so let's, we've got to, we have to take some choices about what to do. And we can't do an infinite number of points for sure. All right, so in all these methods, what we're doing is we're approximating our true f with some approximate f, which is equal to a sum of some basis functions. Sorry about this thing. Like this. So we pick some basis functions. We know how to integrate. We fit somehow determine what these c's are, and then we decide that the integral is equal to the integral of f tilde, not the actual original f. And then that's actually going to be the sum of ck times the integral of vk. And we carefully chose basis functions that we know how to do this integral analytically. So we just plug that in, and we just have to figure out what the c's are to get this to work. Okay, so that's what you really did when you're doing all this trapezoid rule and Simpson's rule and all that kind of stuff. And it's just different choices of what the basis functions were that you used. Now, there's a lot of choices about how to to do that kind of approximation to make f tildes that are sort of like f's with some limited amount of information. And generally has to do with how many k's we have. So if k is less than n, then it's really an approximation, because there's no way we would expect that with just a few parameters we could get a lot of f of t n. So we would expect that f tilde of t n is not equal to f of t n, at least not at all the points. Because if we have a lot of points and we only have a few parameters, we don't expect to be able to fit it perfectly. Okay, so this is what we expect. It might happen if, by some luck, we chose a basis function which was actually the true function f, then it would actually fit perfectly, but most of the time not. Right? By Murphy's law, in fact, it's going to be completely wrong. But this is not such a bad idea. We'll come back to this later. Another possibility is to choose k equals to n, and then we can force f tilde of tn to equal f of tn. So at the points that we have, if we have enough parameters equal to the number of points, then we can get an exact fit. We can force the function to go through all the points. All right, and when we do this, this is called interpolation. Okay. Now, when should you do the one or the other? When should I make k as big as n, or when should I use k less than n? A really crucial thing is whether you really believe your points. If you really believe you know f of tn, like to very, very high number of significant figures, then it makes sense. You know that's true, so you should force your fitting function to actually match that. However, if you get the f of tn, for example, from an experiment or from a stochastic simulation that has some noise in it, then you might not really want to do this because you'll be fitting the noise in the experiment as well. And then you might want to use a smaller number of k's, a smaller number of fitting functions, smaller number of parameters to make the fit. Okay, so you can do either one. You're in charge, right? You get the problem. Somebody tells you, please give me this integral. They don't care how you do it, right? They just want you to come back and give them the true value of the integral. That's, right, to some significant figures. And then, so it's up to you to decide what to do. So you can decide what to do. What a lot of people do in the math world is this one, interpolation, where you're assuming that the f of tn's are known exactly. And so your function evaluating function is great. And in that case, you can write down this nice linear equation. So we're trying to make f of tn, for the true function, to be equal to ck phi n of t. Sorry, phi k of t. And then subtract k is equal to n. And I can rewrite this way. This is like a set of numbers. So I can write it as a vector. I'll call it y. And this thing has two indices on it, so it looks like a matrix. So I'll call that m. And c is my vector of unknown parameters. And wow, I know how to solve this one, right? So c is equal to y backslash n, or m backslash y. Yeah. All right? Now, for this to work and have a unique solution, I need m not to be singular. And what that means is that the columns of m have to be linearly independent. So what are the columns of m? They are phi k of t1, phi k of t2, phi k of tn. Right? And I want that this column is not a sum of the other columns. So this is kind of a requirement for j not equal to k. This is kind of a requirement if I'm going to do this kind of procedure, is I can't choose a set of basis functions that's going to have one of them be a linear combination of the other ones. Because then I'm going to get a singular matrix. My whole process, I'm going to have a big problem right from the beginning. So I have to ensure that this is not true. Okay, yeah, that this is true. These are not equal to some of that. Another way to write that is to write that we want is to choose the columns of phi to be orthogonal to each other. And so I could write it this way. Okay? So I want them to be orthogonal to each other. And then you can see how this kind of generalizes. If I had a lot of t's, this would sort of look like the integral of phi k of t, phi j of t is equal to 0. And so this gives the idea of orthogonal functions. So this is orthogonal functions in my discrete points Tn. And this is the general concept of orthogonal functions. And then when I define it this way, I need to actually decide my own a's and b's that I want to use. And if you use different ones, you actually have different rules about what's orthogonal to each other. And also, sometimes people are fishy and they put a little w of t in here just to do, because they have some special problem where this w keeps showing up or something and they want to do that. But that's up to them. Right? We won't specify that. But this is the general idea of making basis functions orthogonal to each other. And it's very analogous to making vectors orthogonal to each other, which is what we did here. These are actually vectors. Right? It's just as the vector gets longer and longer, it gets more and more like the continuous function. We have more t-points. And eventually it looks like that integral as you go to infinity. All right. So anyway, so a lot of times people will choose functions which are designed to be orthogonal. And one way to do it is just go with the continuous one to start. Now, we can choose any basis functions we want. Over here, we already chose a whole bunch. You guys have done this already. I don't know if you knew you were doing it, but you chose a lot of different basis functions, completely different from each other. You can choose the different ones if you want. And one popular choice is polynomials. But it's not the only choice. And in fact, a little bit later, we're going to, in the homework problem 6, I think we're going to have a problem where you have to use a different kind of basic functions. You can use any basic functions you want, and there's kind of ones that match naturally to the problem. However, people know a lot about polynomials, and so they decide to use polynomials a lot. And so that's the most common choice for numerical integration is polynomials. One thing is polynomials are super easy to integrate, because that was the first thing you learned, right? How to do the integrals of polynomials. And also, they're easy to evaluate. It only takes n operations to evaluate a polynomial of nth order. And there's a ton of theorems and things are known about polynomials. You have all kinds of special properties, and we have all kinds of convenient tools for handling them. So let's go with polynomials for now. Now, I want to warn you, though, that high-order polynomials are really not very good fitting functions or interpolating functions for a lot of problems. And in particular, for this one I showed here, where this is the function up here, that function. You can try to fit that with higher and higher order polynomials. So I can have my function. The function value at 0 is 1. So it's the function looks kind of reasonable. Like that, symmetrical. Better than I drew it. Okay? And you can put some number of points in here. And then you can do an interpolating polynomial that goes through all the points. All right? And if you do it, for this one with 5 points, you get something that looks like this. It goes negative, comes up like this, goes negative again. So that's the one you get if you use 5 points across this interval. If you use 10 points, then you get one that looks like this. Where the peak value here is 2, whereas the maximum of the original function is just 1. And the original function's always positive, but they both go negative. So even within the range of the interpolation, the polynomials can have wild swings. And so this first one was for a fifth order polynomial, or maybe fourth order, 5 points. And this one is for the next, the 10th order or 9th order polynomial. I'm not sure which one. Yeah.
What points are these polynomials trying to fit? It doesn't seem like it fits very good.
So I didn't draw very well. You guys should go home and do this, right? With MATLAB, it'll take you a minute to do the fit, to solve this equation, where you put in the function values here, and put in the polynomial values at the function here for the monomials, t to the first power, t to the second power, t to the third power, whatever, like that. And just do it, and you can get the plot yourself. And just to convince yourself about the problem. This is very important to keep in mind, because we're so used to using polynomials, I think they're the solution to everything, and Excel does them great. But it's not the solution to everything. Nonetheless, we're going to plow on and keep using them for a few minutes. So one possibility when I'm choosing this basis set is I could choose what are called monomials, which is phi k is equal to x to the k minus 1. Okay? And this one is super simple. And a lot of times it satisfies this orthogonality thing, which I showed you before. But it's a really bad choice usually. And what it is that the matrix you have to solve for this interpolation, if you have evenly spaced points and you have x to the k, it turns out that this matrix usually has a condition number that grows exponentially with the number of terms in your basis, the number of how many monomials you include. So condition numbers that grow exponentially is a really bad idea. Okay. So this is not what people use. So you might be tempted to do this, and maybe you did it once in your life. I won't blame you if you did. But it's not a really smart idea. So instead, a lot of the mathematicians of the 1700s and 1800s spent a lot of time worrying about this, and they end up deciding to use other polynomials that have people's names on them. So a guy named, where is his name? Make sure I get this right. So a guy named Lagrange, the same guy who did the multiplier, he suggested some polynomials. They're kind of complicated. They're given in the book. But what they really are is I'm taking the monomial basis set and I'm making a new basis set. So I want phi L to be equal to the sum dLk of phi k, where this phi k is the monomials. Okay, so really you can choose any d you want. You're just taking linear combinations of the original monomial basis set to make up polynomials. And if you cleverly choose the d, you can choose it to have special properties. So Lagrange gave a certain choice of the d that is brilliant in the sense that when you solve the problem m times c is equal to y, to try to do your interpolation, it turns out that the c's you want, ck, is equal to f of tk. So you don't have to do any work to solve what the c's are. It's just the f values directly. No chance for condition numbers, no problems. It's it. So that's the Lagrange polynomials. Now Newton had a different idea. So this is for Lagrange polynomials. If you choose a Lagrange polynomial basis, then this is and you do a square system, that's it. If you choose the Newton, he got into this business too, and he made some polynomials, and he made ones that have a special property that if you solve it. So he chose a different d. You still have to do some solve. You get the solution, and then you decide, I don't like that interpolation. I want to put some more points in. I'm going to do a few more function evaluations. I'm going to add some more. So I have, from the first solve, I have the values of C1, C2, C3, up to C, the number of points I had initially. And now I want to add add one more data point, or add one more f of tn, one more function evaluation. I want to figure out what c of n plus 1 is, what the next one is. It turns out that it's his polynomials, the values of these c's don't change. When I make this matrix a little bit bigger by adding one more y, and I add one more parameter, and I make the one more row in the matrix, one more column in the matrix. When I do that, it's a unique property that none of these other C's change. The solution is going to be the same except for the n plus 1 one. So then I can write a neat, cute little equation just for the n plus 1 one. I don't have to mess with the previous ones. And so I'm just adding a basic function that sort of polishes up my original fit. Okay, so that's a nice property too. So, whereas with the Lagrange ones, you have to recompute everything. And all the C's will change. Okay. All right. Actually, what the C's won't change. I take that back. You add points, the C's won't change, but the actual polynomials will change. The D will change. Because the D depends on the choice of the time points in a complicated way in Lagrange. All right. So now you're starting to think, oh my goodness, I have all these choices. I could use Lagrange, I could use Newton, I could use monomials. Maybe I should, to go back to bed. And you think, well, could somebody just tell me what the best one is? And I'll just do that one. I don't need to learn about all this historical stuff about development of polynomial mathematics. I just like to just tell me what the answer is. So Gauss typically figured out what the best one is. And he said, if we're going to do integrals, we'd really like to just write our integrals this way. So our approximate integral value to be equal to some weight functions times the function evaluations at some times. Right? That's easy to evaluate. That would be good. If I pre-computed the weight functions and the times, then I put any function f in here. I could just do this like a zip. Right? It's one dot product of the f of t n's. I'll have the solution. So I want to do that. So what's the best possible choices of the w's and the t's to make this really be close? Well, the problem is that there's an infinite number of functions that somebody might want to integrate. I can't do them all. So he said, let's just find the one that works for as many monomials as possible to the highest order, as far out as I can go. And it turns out I have n w's, I have n t's, so I have 2n parameters that I can fiddle around with. And so I should get something like 2n's in my polynomials, maybe 2n minus 1. All right, so what I want is that I want to choose this so that for the monomial 1 and the monomial t and the monomial t squared, that this I is actually going to be exact. So what I want is for the monomial 1, I want the summation of wn. My f for the monomial 1 is always 1, so it's times 1. I want this to equal the integral from a to b of 1 dt, which is b minus a. Okay, so that gives me one equation for the w's. Then for the next one, I want the summation wn times t n to equal the integral of a to b of t dt, which is equal to b squared over a over 2, minus a squared over 2 if I did my calculus correctly. And so there's another equation. I have another equation for these guys. And I keep going until I get enough equations to determine all the w's and t's. All right, so I do it for t squared. It's like the wn tn squared is equal to a to b t squared dt, and so on. Okay? And so if you do this process, you get the weights and the points to use that will give you what's called the Gaussian quadrature rule. Now the brilliant thing about this is that by this setup, it's going to be exact for integrating any polynomial up to order 2n minus 1. So if I choose 3 here, I'll be able to determine, if I choose 3 points, I'll have 6 parameters. So I'll be able to determine up to the 11th order polynomial would integrate exactly. Did I do that right? No, that's wrong. I have 3, n is only 3. I have 6 parameters. Can't do this. 2 times 3 minus 1. What's that? 5. There we go. 5 up to the 5th order polynomial. I'll integrate exactly. I'll have an error for 6th order polynomial. So this is a rule. So before, if I gave you 3 points, like here, dunk, 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 most of you probably would do Simpson's rule. Fit this to a parabola. Has three parameters, a, ax squared plus bx plus c, right, for a second order polynomial. I would fit it, then I'd integrate that. That would be the normal thing a lot of people would do. I don't know if you would do that, but a lot of people would do that. So that would be what you get. And what error would you get? You'd have error that would be a scale of the width of the interval to the fourth power, right? Because Simpson's rule is exact up to the cubic. You guys remember this from high school? Delta t, I don't know if you remember delta t to the fourth? Yeah. Okay. So Simpson's rule has error order of delta t to the fourth, but Gauss's method has order of delta t to the sixth. This is for 3 points. And Gauss's method, you can extend it to as many points as you want. All right, so that's kind of nice. You only do 3 points, you get error in the sixth order. So that seems like pretty efficient. So people kept going. And so the very, very popular one is to use actually 7 points for Gauss. So you'd be able to get to the n minus 1. So you'd be exact for 13. So you have delta t to the 14th power is your error. It's pretty good. And then what people often do is they'll add 8 more points. And they make another method that uses all these points. It's called Conrad's method. He made another method that gives you the best possible solution if you have the 15 points, given that 7 of them are already fixed by the Gauss procedure. And so you can get the integral using Gauss's method and using Conrad's method. So you can compute the I using Gauss's method with 7 points, the I with the Conrad method. I don't know how to spell his name, actually. I think it's like this. 15 points. And then you can take the difference between these two. And if these two are really similar, then you might think your integral is pretty good. Because they're pretty different methods. And if they give the same number, you're good. And people have done a lot of numerical studies of this particular case because it's used a lot in actual practice. And it turns out that the error is almost always less than this quantity to the 3s power. So you have an error estimate. So you do 15 function evaluations. You get a pretty accurate value for your integral, maybe, if it can be fit well with a whatever order polynomial. 13th order polynomial. 13th order polynomial, yeah. So any function that can be fit pretty well with a 13th order polynomial, you should get a pretty good value of the integral. And you can check by comparing it to the Conrad estimate, which uses a lot more points. And if the two of these guys give the same number or pretty close, then you're pretty confident that you're good, and there's even a math proof about this particular one. So this is like really popular. And it's a lot better than Simpson's rule, but it's kind of complicated. And part of it is you have to recompute these TNs and WNs for the kind of problem you have. Yeah?
If you're using 15 points already,
yeah.
Why not just split your step size smaller? And if you did that, how would the error, and use the simplest, use, trapezoid.
Trapezoid or Simpson's rule or something like that, yeah.
How would the error with those 15 steps using trapezoid compare to the Conrad Gauss?
So we should probably do the math, right? So it's, say we did Simpson's rule, and we have delta t, and we divide it by 15 or something. Then we can figure out what this is. But it's still going to have the scaling to the 4th power. So the prefactor will be really tiny because it'll be 1 over 15th to the 4th power. But the scaling will be bad. So that if I decide that my integral is not good enough and I need to do more points, I say I double the number of points to get better accuracy, my thing won't improve that much because it's still only scaling to the 4th power. Whereas the Gauss one, say, is going to the 6th power, but I only use the 3 points. Where we use 15 points, it's going to scale some 16th power or 15th power or some really high power. So for doing sequences, the Gauss's one's a lot better. However, what people do is they usually pre-solve the system of equations, because this system of equations does not depend, when you do it with the monomials, it doesn't depend on what f is. You can figure out the optimal t's and w's ahead of time. And so people have tables of them for depending on what order you want to go. People have recomputed them, and then you can get it that way. Time is running out. I just want to jump up. Now for single integrals, I didn't have to tell you any of this because you could have just solved it with your ODE solver, right? So you can just go to ODE-IVP or ODE-IVP, and you'll get good enough. It won't be as efficient as Gaussian, but who cares? You still get a good answer. You can report to your boss. It takes you 3 minutes, right, to call ODE-IVP to integrate the one-dimensional integral. The real challenge comes with the multi-dimensional integrals. So in a lot of problems, we have more than one variable we want to integrate over. And so if you have an integral, say, of a to b from the lower bound of x to upper bound of x, so this is dx, dy, f of xy. This is the kind of integral that you might need to do sometimes. Okay, because you might have two variables you want to integrate over. And so how would we do this? The best way to think about it, I think, is that, right, f of x is equal to the integral of L of x to u of x dy f of x y. And then if I knew what that was, I would evaluate that, say, with a Gaussian quadrature or something. So I'd say that this I2D is approximately equal to the sum of some weights. I'll label them x just to remind you where they came from, times f of xn. And I would use, say, Gaussian quadrature to figure out what the best value of the x's and the y's are to use. And then I would actually evaluate this guy with a quadrature 2. So I'd say f of x k, or xn, is equal to the integral from L of xn to u of xn dy f of xn y. And so this itself, I would give it another quadrature, but this is going to be equal to sum over some other weights, nj f of x and yj. Is that all right? And so this is nested inside this. So now I have a double loop. So if I took me, I don't know, 15 points, 15 function evaluations to get a good number for my integral in one dimension, then it might take me 15 squared operations, 15 squared function evaluations to get a pretty good integral for 2. 15 might be a little optimistic, so maybe 100 is more like if you really want a good number. So 100 in one dimension, 100 in the second dimension squared, so I subdivide the integral into 6 equal pieces, say. And then, now, so this is okay. So you can do this. It's only 10,000 function evaluations, no problem. You've got a gigahertz computer. Now, in reality, a lot of them we do have a lot more dimensions than that. So in my life, I do a lot of electronic structure integrals. We have integrals that are dx1, dy1, dz1 for the first electron interacting with the second electron. And then something that I'm trying to integrate. It depends on, say, the distance between electron 1 and electron 2. Okay? So this is actually 6 integrals. Okay? And so instead of being a 2 in the exponent, this is going to be like a 6 in the exponent. So now this is 10 to the 12th. That means that just evaluating one integral this way might take me 100 seconds if I can evaluate the functions like that. But in fact, the functions I want to evaluate here, these guys take multiple operations to evaluate the function. And so this turns out I can't do it. I can't even do one integral this way with it 6 integrals deep. And so this is the general problem of multidimensional integration. It's called the curse of dimensionality. Each time you add one more integral, you're nested there, all of a sudden the effort goes up tremendously more. You know, a couple orders of magnitude more. And so we'll come back later in the class about how to deal with cases like this when you have high dimensionality cases to try to get better scaling instead of having it being exponential. It's really 100 to the n right now. 100 to the n dimensions. Yeah, can we figure out some better way to do it? All right, thank you.